Okay, while that video was uploading, I did the math here and I got 4.73888 times 10 to the 14th hertz. So that's the threshold frequency, but the question asked for the threshold wavelength. And so I have to go to my C equals F lambda again. Lambda is equal to C divided by F. So, and we're looking for threshold, so we put O's on both of those. So 2.9979 times 10 to the 8th meters per second divided by the 4.7388 times 10 to the 14th hertz. And when I do this, I get a lambda O of 6.3263 times 10 to the negative 7 meters, or that would be 632.63 nanometers if it had wanted it in nanometers. So that's part A. Part B says, what is the kinetic energy in electron volts of photoelectrons ejected, so we're looking for EK max, when 425 nanometer violet light falls on the cesium? So for part B, it's telling us lambda is equal to 425 nanometers. So we can get the frequency of that light, right? So this was the threshold frequency of the surface. This is the frequency of the light coming in. So 2.9979 times 10 to the 8th meters per second, 425 to the negative 9 meters, and we get a frequency of 7.05388, etc., times 10 to the 14th hertz. Okay, we're looking for EK max. And so our main photoelectric effect equation, EK max equals HF minus WO. So EK max is equal to H 6.626 to the negative 34 joules. F 7.05388 to the 14th hertz minus WO. We were given it. It was 1.96 electron volts, and I didn't write it down up there, so I have to do it again. 1.602 to the negative 19 joules per electron volt, right? You can't just leave it in electron volts because that will not end well. All right, so take your 7.06, multiply with 6.626 to the 34, and you get, for the first term, 4.6739 to the negative 19 minus 1.9, it was 6, right? Yeah, times 1.602 to the negative 19. Second term is 3.13992 to the negative 19 joules, and you get an EK max of 1.53398 to the negative 19 joules. The question wants to know in electron volts, so divide that by 1.602 to the negative 19 joules per electron volt. And when you do, 1.602, I missed a number there. That's what the was. 0.9575 electron volts is your final answer. Okay? Now, hopefully these are getting a little bit better. I just wanted to point out something. Now and again, when you do this, you might end up with an EK max that's negative. And if you end up with an EK max that's negative, you have to stop and think about it. What does that mean? It means the HF isn't as big as the WO. That's my phone ringing in the background. We're just going to ignore it. And if the HF isn't as big as the WO, it means the light coming in, it doesn't have enough energy. It will stop in a second. Doesn't have enough energy to release the electrons. That should be the last one on my answering machine should pick up. Okay? Oh, there we go. So whenever you get a negative when you're doing this equation for EK max, just know that it means this isn't going to happen. No electrons are going to be released. They can't be released with a negative energy. Okay? And so if that works out, then you would write, so no electrons are released because the energy of the photon isn't big enough. All right. The next page, over on page 570, I asked you to do numbers 2 to 6. So number 2, the stopping potential, VO. The stopping potential of a certain metal is 5 volts. What is the maximum kinetic energy in electron volts and in joules? So VO equals EK max over Q. So EK max is equal to QV. Oh, well, in electron volts, it's really easy because Q is just 1E and V is 5 volts. So EK max is equal to 5 electron volts. And then changing that into joules, 5 electron volts times 1.602 to the negative 19 coulombs. No, sorry, so used to writing coulombs, joules per electron volt. EK max is equal to 8.01 times 10 to the negative 19 joules. Number 2. Number 3 says, to block the current in a photocell, a stopping potential of 3.8 volts is used. Find the kinetic energy in joules. So VO is equal to 3.8 volts. EK max is equal to Q times VO. EK max is equal to 1.602 to the negative 19 coulombs times 3.8 volts. EK max is equal to, when you do the math, 6.0876 times 10 to the negative 19 joules. Okay, so that's number 3. Number 4. What potential difference is needed to stop electrons having a maximum kinetic energy of 4.8 times 10 to the negative 19 joules? So this time, we're just going in the opposite direction. So this time, we're looking for VO. They've given us EK max, and we know Q. So EK max was what? 4.8? 4.8 times 10 to the negative 19 joules, 1.602 to the negative 19 coulombs. VO is going to be really close to 3. 2.996 volts. Number 5 says threshold frequency, FO, of sodium is 4.4 times 10 to the 14th hertz. How much work must be done? Looking for the work function. So FO, 4.4 times 10 to the 14th hertz. WO is equal to HFO. I'm going to try to get all this in a video, so when you multiply that out, 2.91544 to the negative 19 joules. Number 6 says threshold light of frequency 1 to the 15th falls on sodium in the previous question. What is the kinetic energy? So EK max is equal to HF minus that WO, 6.626 to the negative 34 times 1 to the 15th. And then you're going to minus that 2.9, etc., to the 19th up there. And when you do this, you get an EK max of, gonna run out of time.